For the rest of the unit, we're going to be looking at this concept of enthalpy. Now, the change in enthalpy is the same as saying the heat that is gained or lost at a constant pressure. And so all of a sudden we have a number of different terms for representing energy, the concept that we looked at in the last section. We have enthalpy, we have heat, and then we also have internal energy. Now, internal energy is not the same as saying heat or enthalpy. However, since the difference quantitatively between all three of these is so little, we are going to be using these terms interchangeably. Enthalpy, internal energy, and heat. Enthalpy is the amount of heat absorbed or released by a system. And the way that we actually calculate enthalpy is by looking at the change in enthalpy. So specifically the change in enthalpy, which is represented with a delta H, H for enthalpy, is the difference between the enthalpy of the products and the enthalpy of the reactants. We're now going to look at enthalpies in the context of reactions, which are called the enthalpies of reaction. We represent this with an H for enthalpy and Rxn for the reaction. So the enthalpy of reaction is just the change in enthalpy that occurs during a reaction. And when we incorporate this enthalpy of reaction into the chemical equation, that produces what we call a thermochemical equation. So if you look at this one right here, you have your reaction, and off to the right-hand side, it shows the change in enthalpy, and therefore that makes this a thermochemical equation. These thermochemical equations are crucial when we're trying to calculate the change in enthalpy in more complicated problems. So here are some guidelines for using thermochemical equations. The first one is that enthalpy is an extensive property, meaning that it relies on the quantity of reactants and products that you're using, not their identity. So specifically, if you look at this example, what this is telling you, what this thermochemical equation is telling you, is that 483.6 joules are being released by the system when 2 moles of hydrogen and 1 mole of oxygen react to form 2 moles of water. Now, if instead of 2 moles of hydrogen and 1 mole of oxygen reacted, if 4 moles of hydrogen and 2 moles of oxygen reacted, then the amount of heat that is being released by the system would be double the amount that you have in front of you. In contrast, if we're looking at just 1 mole of hydrogen reacting, then only 241.8 kilojoules would be released. The second guideline that we need to look at is the fact that when you reverse a reaction, when you flip a reaction, you need to multiply the enthalpy of that reaction by -1. So if you look at this example, you have methane reacting with oxygen. This is a combustion reaction in which 890 kilojoules of energy are being released. The reverse of that reaction, the change in enthalpy is actually going to be positive, so it's actually going to be an endothermic reaction. The third guideline states that your change in enthalpy depends on the state of the reactants and the products. So as a result, it's extremely important to note whether each of the substances involved in the reaction are solid, liquids, or gases. This difference can be seen in the fact that the conversion of liquid water to gaseous water requires 88 kilojoules of energy. So if you're producing H2O, like you see up above as a liquid, the change in enthalpy is -890. However, if you are converting it into a gas instead, it only releases -802 kilojoules. So the state of matter, and noting the state of matter, is extremely important because it does change the enthalpy. In order to measure the change in enthalpy, we need to perform an experimental technique that's called calorimetry. Calorimetry is the measurement of heat flow, and in order to measure that heat flow, we need to measure the change in temperature that occurs. Heat capacity, each substance that we will consider has a different heat capacity, and specifically the definition for heat capacity is the amount of heat that's required to raise the temperature of that substance 1 degree Celsius. So each substance has a unique heat capacity. So even if you provide each substance with the same amount of heat, the amount that the temperature changes is going to be different for each substance because they have different heat capacities. There's an important side note that I need to include. If you look at the units here, I said it needs to change in temperature by 1 degree Celsius or 1 Kelvin. The change in Kelvin and the change in Celsius is going to be the same. So if I go from 10 degrees Celsius to 5 degrees Celsius, if you converted that into Kelvin and calculated the change in Kelvin, it's still going to be the same difference. It's still going to be 5 degrees Celsius or 5 degrees Kelvin. And that's because in order to go from Celsius to Kelvin, you simply have to add 273. So change in Kelvin and change in Celsius is the same. Now there are two other types of heat capacity that we need to consider. The first one is molar heat capacity. Now the molar heat capacity is just the heat capacity of 1 mole of a substance, while the specific heat capacity is the heat capacity of 1 gram of a substance. Since specific heat capacity is a much larger name than simply heat capacity, if we're talking about the specific heat capacity, we often just say the specific heat of a substance. You will see the difference between specific heat capacity, molar heat capacity, and just heat capacity in the units. Because if the units involved either grams or moles, then you have either the specific heat or the molar heat capacity. If it does not include moles or grams, then you simply have heat capacity. So here is the formula for calculating the heat that is involved when you have a temperature change. Q is your heat, your CS is your specific heat, M is your mass, and delta T is your change in temperature, which can either be in degrees Celsius or Kelvin. So what this formula allows you to do is to either calculate the heat that is either gained or lost when temperature changes in a substance, or you can actually calculate the change in temperature that accompanies a specific heat being transferred, or you can calculate the specific heat of a substance. So there are a lot of different things that you can calculate using this formula. So here's one example for you. It tells you that you have 250 grams of water, and it tells you that you're changing your temperature from 22 degrees Celsius to 98 degrees Celsius. It tells you that the specific heat of the water is 4.18 joules per gram degree Celsius, and it's asking how much heat is needed to warm that. So you're searching for your Q. Notice briefly that the units for your specific heat include grams, so that's how you know it's specific heat. If it were just joules per degree Celsius, then that would just be your heat capacity. So I'm searching for my Q. So I know my specific heat of water is 4.18 joules per gram degree Celsius. I know that the mass is 250 grams, and I can calculate the change in temperature by subtracting 22 degrees Celsius from 98 degrees Celsius, because 98 is your final temperature and 22 is your initial temperature. So if you subtract TF minus TI, you get 76 degrees Celsius. Now when you multiply this, you get 79,420 joules. Notice the grams cancel and degrees Celsius cancel. However, since 76 only has 2 sig figs and so does 250, I would round this to 79,000 joules. If I didn't want it in joules and instead wanted it in kilojoules, all I would have to do would be to divide by 1,000, and that gives me 79 kilojoules.